A black hole is a region of spacetime where gravity has become so intense that the escape velocity exceeds the speed of light itself, so that nothing, not matter, not light, not any signal whatever, can cross outward through its boundary. That boundary, the event horizon, is not a wall or a surface made of anything. It is a one-way causal membrane, the set of events from which no future ray of light can ever reach a distant observer. Cross it, and the outside universe is closed to you forever. Black holes are the most extreme prediction of Einstein's general theory of relativity, and in this chapter we follow the physics of strong gravity from its mathematical foundations all the way to the frontier puzzles, where gravity, quantum mechanics, and thermodynamics collide. They are, as we shall see, the most productive natural laboratory we possess for probing the very deepest laws of nature. The concept is older than relativity. As early as 1783, the English clergyman John Michell, and independently the French mathematician Pierre-Simon Laplace a little over a decade later, reasoned on Newtonian grounds that a star sufficiently massive and compact would have an escape velocity greater than that of light, rendering it a dark and invisible body. But the modern theory is purely relativistic, and it emerged from the general theory of relativity that Einstein completed in November of 1915. General relativity replaces Newton's force of gravity with the geometry of a curved, four-dimensional spacetime. Matter and energy tell spacetime how to curve, and the curvature of spacetime in turn tells matter how to move. The coupling between them, expressed in Einstein's field equations, is extraordinarily weak, which is precisely why the curvature of spacetime becomes significant only for the densest and most massive systems in the universe, and why black holes are such exotic objects. Black holes come in several distinct mass ranges, and every one of them is now supported by observation. Stellar mass black holes, from roughly 3 to 100 times the mass of the Sun, form when the cores of massive stars collapse at the end of their lives or when compact objects merge. The lower limit follows from the failure of neutron pressure above about 2 to 3 solar masses, beyond which no known force can halt the collapse. Supermassive black holes from millions to tens of billions of solar masses sit at the centers of galaxies. Our own Milky Way hosts one called Sagittarius A star, with a mass of about 4 million suns. How such giants grew so massive so early when we already see quasars blazing in the first billion years of cosmic time is an open question. Intermediate mass black holes, and primordial ones that may have formed from density ripples in the infant universe, are proposed but far less firmly established. For decades, black holes remained a contested mathematical curiosity, and many physicists, Einstein and Eddington among them, hoped that real, slightly irregular collapse would somehow avoid so pathological an endpoint. That hope was dispelled in 1965, when Roger Penrose proved, using powerful new topological methods and the idea of a trapped surface, that collapse to a singularity is generic and unavoidable, not an artifact of perfect symmetry, work for which he shared the 2020 Nobel Prize in Physics. 3 landmark observations have since carried black holes from theory into hard reality. In 2015, the advanced LIGO detectors recorded the gravitational waves of 2 black holes merging more than 1 billion light-years away. In 2019, the Event Horizon Telescope released the first image of a black hole's shadow at the heart of the galaxy Messier 87, and in 2022, that same global instrument imaged our own Sagittarius A star. The mathematics began within weeks of Einstein's equations. The German astrophysicist Karl Schwarzschild, serving on the Russian front in the First World War, found the first exact solution and sent it to Einstein in December of 1915. He would be dead within months of an illness contracted at the front. The Schwarzschild solution describes the empty, curved spacetime outside any static, spherical, non-rotating mass, and by a theorem of Birkhoff, it is the unique such solution, which means the external field of a non-rotating star, of a collapsing shell, and of a black hole of the same mass are all identical. Its central quantity is the Schwarzschild radius, twice the mass, times Newton's constant, divided by the speed of light squared, which works out to about 3 kilometers for every solar mass. A black hole of 1 solar mass has a horizon barely 3 kilometers across. To turn the Earth into a black hole, you would have to crush it down to about 9 millimeters. The Schwarzschild geometry has 2 apparent trouble spots, and telling them apart is essential. At the Schwarzschild radius itself, the equations seem to misbehave. But this turns out to be only a defect of the particular coordinates, an illusion that vanishes when better coordinates are chosen, coordinates in which the geometry is perfectly smooth right across the horizon. An astronaut falling through the horizon of a large black hole would notice nothing special at the moment of crossing. The tides there are finite and, for a supermassive hole, gentle. The genuine singularity lies at the very center, where a coordinate-independent measure of curvature truly diverges to infinity, signaling infinite tidal stresses and the outright breakdown of classical general relativity. Inside the horizon, remarkably, the roles of space and time interchange, so that reaching the central singularity becomes as inevitable as reaching next Tuesday. Whether such singularities are always decently hidden behind horizons, Penrose's cosmic censorship conjecture, remains unproven to this day. The observable effects of this geometry follow from the way light and matter move through it, along the straightest available paths in curved spacetime. One consequence is immediate and profound: gravitational time dilation. A clock held at a fixed distance from the hole runs slow compared with one far away, and light climbing out of the gravitational well is stretched toward longer, redder wavelengths, the gravitational redshift. As the source approaches the horizon, that redshift grows without limit. To a distant observer, an infalling clock appears to slow, to redden, and to freeze at the horizon, its final image fading and dimming but never quite winking out. This effect is minuscule but measurable near the Sun and near white dwarfs, and it becomes extreme in the neighborhood of a black hole. It is the very same effect, incidentally, that the engineers of the global positioning system must correct for, since clocks aboard the satellites tick measurably faster than those on the ground below. Light itself does not travel in straight lines near a black hole. There exists a photon sphere, a radius at 1.5 times the Schwarzschild radius, where light can in principle circle the hole on an unstable orbit. Photons, grazing that region, loop around once or many times before escaping, producing the bright ring that outlines the black hole's dark shadow in the Event Horizon Telescope images. Because of how strongly those rays bend, the shadow a distant observer sees is larger than the horizon itself, about 2.5 times the Schwarzschild diameter, a specific prediction confirmed by the pictures of both Messier 87 and Sagittarius A star. For matter, the crucial radius is the innermost stable circular orbit at 3 times the Schwarzschild radius. Inside it, no stable orbit exists at all, and matter spirals rapidly inward. That radius marks the inner edge of any accretion disk, and it fixes the astonishing efficiency of accretion as an energy source. Just how efficient depends on the black hole's spin. For a non-rotating hole, matter slowly spiraling inward can radiate away nearly 6% of its rest mass energy before it crosses the point of no return, already far more than the 0.7% released by the hydrogen fusion that lights the stars. For a maximally spinning black hole, the innermost stable orbit moves much closer in, and the efficiency rises to a remarkable 42% of rest mass energy. This is why accretion onto black holes powers quasars and active galactic nuclei, the most luminous persistent objects in the entire universe. In practice, the brightness is capped by the Eddington limit, the point at which the outward pressure of the radiation balances the inward pull of gravity and blows away any further infalling gas, a natural ceiling that also limits how fast a black hole can grow by swallowing matter. Real astrophysical bodies rotate, and the conservation of angular momentum guarantees that collapsing stars and merging black holes spin rapidly, so the non-rotating Schwarzschild case is really an idealization. The general solution for a rotating black hole was found in 1963 by the New Zealand mathematician Roy Kerr, almost half a century after Schwarzschild, in a famously brief and brilliant paper. A Kerr black hole is specified by just 2 numbers, its mass and its angular momentum, and its spin can range from 0 up to a maximal value, beyond which no true black hole can exist. Its defining new feature is frame dragging, the Lenz-Thirring effect. A rotating mass drags the very fabric of spacetime around with it, so that any particle dropped from rest, even one aimed straight down, is swept into rotation in the direction of the spin. Space itself is set turning around the hole. The rotating solution has a far richer structure than its static cousin. Where the non-rotating hole has a single horizon, the Kerr hole has 2, an outer event horizon and an inner one, which merge together in the extremal maximally spinning case. Push the spin beyond that maximum and the horizons vanish altogether, exposing the singularity to the outside universe. a so-called naked singularity, which cosmic censorship forbids, and which is believed to be unreachable by any physical process that tries to spin a hole up past the limit. Measurements of real black hole spins, drawn from X-ray spectra and from the ringing of newly merged holes, indeed cluster below that bound, with some supermassive black holes inferred to be spinning very nearly as fast as they possibly can. And the Kerr singularity is not a point but a ring, a structurally stranger object, whose idealized interior even hints at passages to other regions of spacetime, passages that are almost certainly destroyed by any real perturbation. Surrounding the outer horizon of a spinning black hole is a second remarkable surface, and between the two lies a region called the ergosphere, from the Greek word for work. Within it, frame dragging is so overwhelming that no observer, no particle, not even a beam of light, can possibly remain still with respect to the distant stars. Everything is compelled to co-rotate with the whole. But, and this is the crucial point, the ergosphere lies outside the event horizon, so one can enter it and still escape again. In 1969, Roger Penrose showed that this makes it possible to extract energy from a rotating black hole, send a body into the ergosphere, split it in two so that one fragment plunges through the horizon on a trajectory of negative energy, and the other fragment flies back out carrying more energy than the whole body brought in. The difference is paid for by the hole itself, whose spin and mass both diminish. The bookkeeping was made precise in the early 1970s through the idea of an irreducible mass, the portion of a black hole's mass that can never be reduced, tied directly to the area of its horizon. For a maximally spinning black hole, as much as 29% of the total mass energy is stored in rotation and can, in principle, be mined, while the irreducible mass, and with it the horizon area, can never decrease in any classical process. The Penrose process has a wave analog called superradiance, in which a wave of just the right frequency, scattering off a spinning hole, comes away amplified, having stolen rotational energy. And it has an electromagnetic cousin, the Blandford-Znajek mechanism, that matters enormously in the real universe. Magnetic field lines threaded through a spinning horizon are twisted by frame dragging and fling rotational energy outward as colossal jets. The relativistic beams that power active galactic nuclei and gamma-ray bursts. By the early 1970s, a striking pattern had emerged, a formal parallel between the mechanics of black holes and the laws of thermodynamics. Stated by James Bardeen, Brandon Carter and Stephen Hawking in 1973, the four laws of black hole mechanics ran uncannily close to the four laws of heat. A zeroth law, the surface gravity is the same everywhere across the horizon of a settled black hole, just as temperature is uniform throughout a body in equilibrium. A first law relating small changes in the hole's mass, area, spin and charge, exactly mirroring the conservation of energy in ordinary thermodynamics. A second law, Hawking's area theorem, declaring that the total horizon area can never decrease, so that when two black holes merge, the final horizon exceeds the sum of the originals, echoing the ever-rising entropy of the universe. And a third law, forbidding the reduction of surface gravity to zero by any finite process. The correspondence was term for term, surface gravity playing the role of temperature, and horizon area the role of entropy. At first this looked like nothing more than a suggestive analogy. A classical black hole, after all, absorbs everything and emits nothing, so its true temperature is absolute zero, and to assign it a real entropy seemed a plain category error. Hawking himself was among the skeptics, but the graduate student Jacob Bekenstein pressed the point. Drop a hot gas carrying entropy into a black hole, he noted, and that entropy simply vanishes from the outside world, apparently decreasing the total and violating the second law of thermodynamics. To rescue the law, Bekenstein proposed that the black hole itself must carry an entropy, one proportional to the area of its horizon. The final formula, completed by Hawking's work, is among the most remarkable in all of physics. The entropy of a black hole is 1/4 of its horizon area, measured in units of the tiny Planck area. Astonishingly, it scales with surface area, not with volume. A black hole's capacity for information is set by its bounding surface, an insight that grew into the holographic principle and reshaped the whole field. The clinching result came in 1974. If a black hole truly has an entropy and truly obeys the first law, then it must possess a real non-zero temperature, and anything with a temperature must radiate. Applying quantum field theory to the curved spacetime around a collapsing star, Stephen Hawking proved that a black hole is not perfectly black at all. It emits a faint thermal glow, now called Hawking radiation, with a temperature inversely proportional to its mass. A common heuristic pictures pairs of virtual particles flickering into being at the horizon, one falling inward with negative energy while its partner escapes as real radiation, though the true derivation is subtler, involving the way the quantum vacuum's modes are scrambled between the distant past and the distant future. The radiation carries energy away, so the black hole slowly loses mass and shrinks, and because a smaller hole is a hotter hole, the process quietly accelerates as it runs. The numbers explain why we have never detected this glow from any astrophysical black hole. A hole of one solar mass has a Hawking temperature of about 60 billionths of a degree above absolute zero, and a supermassive hole is 1,000,000 times colder still, far, far colder than the 2.7-degree afterglow of the Big Bang that bathes all of space. Such black holes therefore absorb vastly more than they radiate and are still growing, not evaporating. The time for a solar mass hole to evaporate away completely would be some 10 to the 67th power in years, unimaginably longer than the present age of the universe. Only primordial black holes of modest mass, formed in the earliest moments, would be reaching their explosive end around now, in a final burst of gamma rays, and searches for such bursts have so far yielded only upper limits. Strikingly, black holes have a negative heat capacity. Losing energy makes them hotter, the very reverse of an ordinary star, which is exactly why an evaporating hole can never settle into equilibrium, and instead runs away to its final flash. Hawking's discovery opened a paradox that has haunted physics ever since. Quantum mechanics is unitary, information is never truly destroyed, and a pure quantum state can only ever evolve into another pure state. Yet Hawking's radiation is exactly thermal, featureless, depending only on the hole's mass, its charge and its spin. This is the content of the no-hair theorem, that a settled black hole is described by just those three numbers, every other detail of whatever formed it having radiated away during its birth. So if a black hole forms from a book, or an encyclopedia, or a collapsing star, and then evaporates entirely into that featureless thermal static, the detailed information about what fell in appears to be erased from the universe altogether. A pure state would have evolved into a mixed one, and that is forbidden by the very quantum mechanics used to derive the radiation in the first place. This is the black hole information paradox. The paradox was sharpened into a precise benchmark by Don Page in 1993. If evaporation truly preserves information, then the entanglement entropy of the escaping radiation must trace out one particular shape, the Page curve rising as radiation is emitted, then turning over at the halfway point and falling back to zero as the last quanta carry the encoded information away. Hawking's original calculation, by contrast, gave an entropy that only ever rose, the unmistakable signature of information lost. Reproducing the Page curve from gravity itself became the concrete goal. The most significant recent progress around 2019 and 2020 showed that it can in fact be done, using a technique called the quantum extremal surface, together with a startling new ingredient, regions deep inside the hole, called entanglement islands, whose contents are counted as part of the outside radiation. Physicists recovered exactly the Page curve. In the gravitational path integral, new geometries known as replica wormholes take over at late times and bend the curve back down. The paradox is now substantially clarified, though not yet in full resolved. Step back, and black holes are seen to knit together the three great pillars of modern physics more tightly than any other subject. The Schwarzschild and Kerr metrics give the exact classical geometry. The four laws and the entropy formula reveal that this geometry is secretly thermodynamic. Hawking radiation shows that the thermodynamics is quantum in origin, and the information paradox shows that a fully consistent account demands a theory of quantum gravity we do not yet possess. What was once pure speculation is now precision observational science anchored by three great programs. Gravitational wave astronomy tests the Kerr metric directly, listening to the ringdown of newly merged holes for the tones that should depend only on final mass and spin. A direct test of the no-hair theorem, so far past, within the uncertainties. The Event Horizon Telescope has resolved the shadows of two separate black holes, and decades of tracking stars whipping around Sagittarius A star, honored with the 2020 Nobel Prize, pinned down the 4 million solar mass dark object at the very heart of our galaxy. Yet a great deal remains genuinely and importantly open. the ultimate endpoint of evaporation, and the final fate of information await. The missing theory of quantum gravity. Whether cosmic censorship truly holds, always clothing singularities in horizons, is unproven. The interior of a real rotating hole, the stability of its inner horizon, and the true nature of the central singularity are not understood. The microscopic origin of the entropy, what precisely the black hole's countable states are, is known only in special, idealized cases, whether primordial black holes exist at all, and whether they might make up some fraction of the dark matter, is unsettled, and the detailed mechanism by which spinning holes launch their enormous jets is still being tested against the data. Across every test yet devised, general relativity has passed without a single deviation. Black holes remain what they have been for 50 years, the most extreme laboratory in all of nature, and the clearest signpost we have toward the physics that lies beyond Einstein.